IFAC Computational Intelligence in Control, Steering Committee, member of the ASEAN Control Association, member of the IFSC Council and Vice Chair of the IEEE Technical Committee on Consumer Electronics, Power and Energy. He serves as an editor with IEEE Transaction on Sustainable Energy, IEEE Systems, Journal, IEEE Access and IET Electronics Letter. His research interests include system and control of power system, embedded system, and AI and machine learning. He has supervised as his 45 PhD students, published 164 peer-reviewed journal papers, 110 papers in conference proceedings, 14 book chapters, and 8 books. Now I request Professor Bidyadhar Subudhi sir to address the session. Thank you, sir. Please, sir.
Thank you, the organizers, in particular the General Chair and NIT Warangal, for inviting me in this session to give my experience on the control of microgrid. And so, is there any slide projector? This one is working. So, the topic I have chosen for today is robust and adaptive control of microgrid. Yeah. It can be operated here. Okay. So I'll be speaking on the three aspects. One is the control problem associated with microgrid. And then the other one is there are two control we devised which is of interest to you, I believe. One is dynamic average consensus based distributed control, and the second one is basically the adaptive backstepping control. So all of you know that this microgrid is a small power network with a cluster of loads and some distributed generating units like photovoltaic or wind or any renewable energy sources you mean. And there is a coordination among all these DG units. They are participating in the microgrid, and also there is a there is a set of communication and also the computing inbuilt. So why this microgrid is so important today? Because you may consider that no matter whatever we generate the energy, but if there may be difficulty in integrating all of them, like as I was saying in my inaugural address, suppose there is a big power plant with renewable energy like 1 megawatt photovoltaic power plant. Now what happens, let us say the grid fails. In that moment, if without a reference signal, you cannot use that 1 megawatt power. You cannot push in power. So therefore, there is a need to restructure the power system. One of the ways can be done with a microgrid. So you can tailor all of them into your load in a microgrid and connect the microgrid to the main grid. So therefore, you have the choice when you can use it as islanded mode or a grid connected mode. And of course, it has a grid management software and also some controllable loads like electric vehicles, etc. And a robust communication network, because this microgrid is considered as a tiny unit for a smart grid. So therefore, communication is a must there. And obviously, by microgrid adoption, we can reduce the big infrastructure toward the transmission distribution in a large power plant. And of course, that facilitates the integration of renewables, as is quite obvious. And the power quality and reliability can be ensured very easily compared to a bigger power system, a centralized power system. And of course, this last point is very important. No matter whatever serious you are, you cannot avoid the blackouts. But even you have the microgrid, at least blackouts can be avoided because you have a localized power generation and utilization is there. So the figure on the right, as you could see, a couple of distributed generating sources and the fossil fuel based sources, and that I represented as DER1 to DERN, meaning distributed energy resources 1 to n, and they are connected to point of common coupling to a microgrid network, and then the main grid through a connection either back and forth. Either you can connect in a grid connected mode or a standalone mode. Now, what are the control problem that we expect or in a microgrid for its operation? As you could see the figure in the right, the from the input the kind of renewable energy sources. So, for example, there is a photovoltaic source. So the irradiance level is not constant. We cannot expect it. It is very intermittent in nature. And the wind velocity in case of a wind energy system. So these are very intermittent. So this is one input side is there is a problem. Sorry. Okay. And then if you could see the from the control side also, when you want to get the control, as I said that the communication is inbuilt, there could be packet dropouts, there could be communication delay, latency. So there could be denial of services, there could be cyber attacks, and so many polytronic converters are there. So therefore, there could be some switching function of the polytronic converters. All of them contribute some kind of challenges in microgrid control. So therefore, I listed the problem that we encounter in the control aspect of the microgrid. One of them, the stability issues, like the local oscillation that may emerge from the interaction of the control system and the DG units. So we have to have a small disturbance stability analysis is needed for that. And we should have a transient stability analysis to ensure a seamless transition between the two modes of operation. And of course, the modeling is a little difficult rather than what we do a conventional power system because of the assumptions you have to relax all the time, the constant power load, etc. You may not assume. And of course, this is the third one is more challenging. Like the droop control in case of a microgrid is much difficult than in a classical grid. Why? Because in the classical grid, the most of the generators there in the loop, they have high inertia. Because of high inertia, the droop control becomes little easier. But in case of microgrid, the renewable sources along with the polytronic devices, they have the low inertia. And therefore, you have to mimic the situation of the synchronous generator. Your control should mimic, just like synchronous generator has a high inertia, that kind of mimicking is necessary to implement the control. And of course, the uncertainty, as I mentioned, a lot of uncertainties and disturbances are there in the system. And also the output control, like how to maintain their output voltage of the DG units, the distributed energy resource units participating in the grid, also their frequencies at the nominal values, the grid or PCC values. And there could be the power balance, the power sharing among these participating units. Of course, the economic dispatch is also to be taken into account, and the transition already I mentioned. So these are some of the issues we need to address. So therefore, if I summarize all the control challenges, so the control task, I mean there are four essentially control tasks involved in the microgrid. One is the frequency and voltage regulation, meaning let us say in a microgrid there are 10 number of DG units. The output voltage and the frequency of those DG units should be regulated at the nominal values of the grid. That is one task. The second is the active and reactive power control between the DG units and main grid. What is the sharing according to the ratings? And if some of the DG is out of order, how the remaining one will take care of it and how the transients will go down. And then the other thing is the synchronization of the microgrid with the main grid. Okay, and then the next control task required is the optimal use of the microgrid. So all of these control tasks, the four tasks, are accomplished in a hierarchical control. So what is the meaning of hierarchical control? There are three levels of control. One is called the primary level control, secondary level control, and tertiary control. And the primary control is the level 0 control, which is responsible to stabilize the frequency and voltage subsequent to a islanding condition. And they, as I said, they mimic the behavior of a synchronous generator for the droop control, PQ, the active power and reactive power control. And the secondary control is that which restores back the normalcy that has been caused in the primary loop, and also to provide the nominal value, the voltage and frequency values for the secondary control. Of course, the tertiary control is the highest level of control in which the economic operation of the grid is decided. But here only one point one has to observe, their time scales are different. Primary control to the top, if you go, the tertiary control is the, the level, it is a fast control basically. Now, what I want to tell you is that our focus is to design some controller in the secondary loop. So what is the objective here? The objective is that, let us say there are n number of DG units, and ith DG unit output voltage is VNI, and ith unit DG unit has the frequency omega Ni. What is the purpose here? The purpose is to synchronize all these DG unit voltage and frequency to the respective nominal values. That means all n number of DG output voltages should be regulated at the nominal value of V nominal and nominal value of the omega nominal. That is the objective. Now, this secondary control can be done in two ways. There are two control paradigms usually. One is called centralized control. The second is the distributed control. The meaning of the centralized control is that where all the DG units are associated only one control. All DG units are controlled only by one central controller, right? Secondary controller. So what happens if there is a fault in that the centralized controller? So there is a single point failure. The entire system will not work. Or on the contrary, if you see the second one, the distributed control, each DG unit is accompanied by its individual secondary controller. So in the event, let us say particular DG unit is the controller is not working, so remaining are still in the loop, so single point failure could be avoided. So this is, so therefore secondary control in the distributed structure is our. So this is the diagram that clearly shows. The left one is basically the centralized control, as you could see. The RES means renewable energy source, and then there is a converter there. So that represents a DG unit. And it is have a primary controller, and all of them are communicated with a communication network to a secondary control. But on the other hand, in this distributed control, you could see each DG unit has a primary controller and a secondary control. Now, what is important in this topic of discussion today, that the prime objective is to design a set of adaptive and robust controller. What is the need? As I said, the microgrid has a lot of challenges in control perspective. One is the solar irradiance or the renewable energy is not constant. So there are some uncertainties there. And the polytronic devices, they also contribute some kind of uncertainty in terms of their PWM switching function or something like that. And there could be something like the load disturbances, plug and play operation. So many disturbances maybe are in the system. And the cyber system, like the communication failure, packet dropouts, so many things are there. So in face of all those, we need to design some kind of adaptive controller. That is the need of adaptive controller. And why robust controller? Because the robust controller are those which give you the satisfactory performance in face of the uncertainties. So therefore, these are the two controllers we are interested. And the right side of it, you could see, it is the diagram of ith DG unit, meaning one DG unit is accompanied by a voltage source inverter, a filter, and it is connected to the point of coupling. And we have the, the primary control and the secondary control with the communication network inbuilt. Now, what is more important here? One of the advantages of the secondary control is that, as I said, that each DG unit is connected with a its own secondary controller. So we take the advantage of putting a communication network there. All the DG units are communicated by a communication network. Now imagine in a microgrid there are several sources, photovoltaic sources or wind sources, whatever. and their power electronic devices, communication network. So all these components, if you think that any control can be designed to make a consensus to achieve. So one of the nature driven idea is borrowed here. What is the nature driven idea? If you could see in the sky in the evening, you could see a lot of birds, they are making a flock. So one of the bird is behaving as a leader and the remaining birds are behaving as followers. So what happened? There is a communication among them. So might be the leader bird could be given the information about the trajectory, it goes to the nest. So all other local information will happen from the leader bird to the follower bird. So the same, and similarly if you see the school of fish in a pond, one fish is behaving as a leader and the remaining are behaving as the followers. So this group behavior gives an indication that you can design a consensus based control putting a communication network within it. So therefore we get a inspiration from there. And you could see now the microgrid, all these components, as I said, the photovoltaic source or wind source or what you call the distributed energy resources and the power electronic converters and then the communication, each component you assume to be one DG unit or agent, one agent. If you assume them as one agent and put a communication network and there could be the information can be shared by some sensors, then put a communication network, then that communication network can be translated as a directed graph. That means if the agent 1 to agent 2 there is a communication, then there must be some weightage. If not, you will consider it differently. So then the idea is that we use this is called multi-agent system theory, which is very, very important for designing a cooperative control. Now what you do in this microgrid, we consider a number of DG units and we consider a communication network. So what is the idea here? As you could see the figure, like there are n number of DG units. These n number of DG units are communicated through some kind of communication link and they are represented by a diagraph, communication graph. And then what happens? We find three things here. One is the Laplacian matrix, that is L, and integral matrix, that capital D, and the adjacency matrix is A. How to do that? You represent the communication by these matrices. So for example, if DG1 and DG2 are connected, then A12 the strength is 1, otherwise it is 0. Like that the elements are filled in that AG matrix. And if you could see, all the rows sum of A matrix appear as the D matrix, right? And then L is found out D minus A, so that is called the Laplacian matrix. Okay, so now what is the idea here? The idea is that we consider each component of the microgrid as an agent and we consider it as a single integrator dynamics, that is xi dot equal to u. So if you take that, then let us say ith DG unit state is xi and the neighboring DG unit state is xj. So the purpose is that you should get a consensus if this xi and xj tend to a consensus value. So therefore we can design a control called consensus control. That is the idea here. Now what you do, that DG unit, the ith DG unit, we model it. Like you see, a renewable source with a PWM converter with a VSI, LC filter, then it goes to the PCC. Then what we do is we design two controllers. One is called current controller and a voltage controller. So those are, before that we have to calculate the power, both active and reactive power, because you have to implement the droop control. And these equations, like you see, so this whatever you take from the output ABC frame, you convert to DQ frame for simplicity. Then once you do that, then the D respective voltage and current in the D and Q axis are found out. Then corresponding equations for power calculation are employed. Then using a filter with a filter frequency omega c, you get the active and reactive power. Now the droop equations are taken. Now the objective is to pick up the droop coefficients in a way, adjust them in a way so that by varying P, you can vary the frequency, and by varying Q, you can vary the voltage. So that's what is the idea. Now those two equations we want to implement. So what is that? So we then calculate the apparent power supplied by the microgrid to the the boss. So basically the apparent power you calculate V boss multiplied by I boss and separate the real and imaginary parts. Then the active power and reactive power are calculated. Then we assume the power, you see the right side figure, the transmission line we consider as an inductive transmission line. And therefore this angle theta becomes 90. And then these two equations are simplified, and again we assume that the angle phi, this is the impedance angle at the output voltage, so that angle is also very small, so therefore the cos phi is 1 and sin phi is phi. So what it gives the idea? It gives the idea that these two equations are further simplified as pi is related to phi and qi is related to v. And so then the linear relationship we get that in order to control P, you have to control phi. In order to control Q, you can control the voltage. Simple. So then these two analogy we have taken for the droop control. So the idea is that you want to vary the frequency in a way from the omega n, the nominal frequency, to the new nominal frequency, so that whatever deviation has been caused in the primary loop has been taken care by the secondary loop. Similarly, you see the second equation, droop equation, that is V equal to Vni minus Kq Qi. So your job is to change this, you have to vary this voltage Vn to new voltage, so that whatever the deviation is being caused in the primary control would be taken care in the secondary control. So now the control design starts, like the control name is dynamic average consensus based distributed control. I said that all the DC units is provided with a secondary control, distributed manner. So the control problem is that we have to control the voltage and the frequency across the output of individual DC units to a nominal value. That is the objective. So in order to do so, that means VOI, that is the output of the ith DC unit, should be maintained at V nominal. And similarly, the output of the omega, the output frequency of the ith DC unit should be maintained at omega nominal. Now what you do, we have the droop equation as I discussed earlier. So you manipulate those equation in this manner. That is, you differentiate it, then take the little manipulation, you come out with the equation omega ni, integration of that, and Vni. Now if you choose two control inputs, one is the voltage, another is the frequency. So from that equation, so that Vni dot and omega on the left side of it. So these are the control inputs. So if you choose these control inputs, then you can vary this. So then you can vary the control. So what happens here is that, so now these equations, now as I said, the consensus based control is a single integrator dynamics of the agent we have considered, that is xi dot equal to ui, and there are n number of agents. Now this state of the agent, that means for ith agent it is ith xi, for the jth it is either a voltage or a frequency. Now what you do, you design a control based on that consensus based control. So where you need to have the graph, that Laplacian you need to find out that, and all the others are constant. Xj is coming from the neighboring DG, and this Vi is the reference, voltage reference. So these detail you can find out from this paper IT Smart Grid. And then all these equation, this equation, there are two such, because one equation we can develop for the voltage, one for the frequency. So the corresponding voltage equation, so you see here, the Ri we replaced by V nominal. And then rest of the things, this is omega, this xi dot equal to Vi dot, because Vi voltage you want to control. So then this equation came, and this equation you translated to this block diagram, right? This is the structure. Now similarly for frequency, another structure came. Two structure came. Now what is happening here? But these two control equation, they do not take care of the latency of the communication network. So what he did is, we negated the time delay, that is meaning the communication delay if there in the system. So therefore this is the new control law, and we also put a limit how much delay it can tolerate. That limit we defined from the graph, because communication related to the communication network of the graph. Now what we did is, we verified this control for a test system. In the test system, what you did, we take 5 DG units, and we take some loads, 1, 2, 3, 4, 5 loads. These are the line impedances, and we put them two communication topologies. One is a ring topology and other is a radial topology. In the ring topology, we have chosen these, the same leader and follower approach. And then the radial topology, the connection is like that. So we have taken some specification of the microgrid system. And then these are the different DG units, nominal voltage, and then the filter coefficients and the control gains, line impedances and load impedances. Then what we did, we implemented this controller. What you see here, the primary control is always active, and at t equal to 1.5 second, we made the secondary control active. Now what happens? So at 2.5 second, load 1 is increased. As a matter of fact, the voltage drops, and similarly the frequency also drops. So this transient for a while persists because of the secondary control. So all these are restored back to the normal values, nominal values, and the corresponding active and reactive powers are changed. Now similarly what we did, the similar performance we get, meaning when you employ a secondary controller, the output voltage and frequency are regulated in nominal values, despite there are the changes in the communication topology. You change initially to you change to radial topology, still the transients are died down. Now we also compared the efficacy of the proposed controller with respect to an earlier controller which is reported in this paper, and the proposed one is a blue response, blue colored response, in which, as you could see, the oscillations are less compared to the existing controller. And then we also verified the effect of handling the communication delay by the proposed controller. That means, as you could see, here the delay is 0.1 second. Now the delay is increased to 1 second. Now delay is further increased to 2 seconds. These delays are basically the communication delay or latency. Now you could see for 0.1 second it is very smoothened, and the output is taken for 1 DG unit. But if the delay is increased, you could see that the overshoot is here, some transient is here. Now if you increase the delay further, you see more transients are there, meaning the controller has a allowable range of controlling the or compensating the delay. Now what you do, we have also verified the scalability issue. What is the scalability issue? Scalability means we applied the same control for a IEEE 39 bus system, and you see still there are around 39 bus. The DG units, output voltage and current frequency are regulated at the nominal values, and then we can. So therefore, this control can be applied to bigger systems. Now here, you see, now at 2 seconds the controller is activated. At 3 seconds the DG number 5 is disconnected, and therefore there is a little transient here. And again t equal to 4 seconds it is brought back. So even then there is a transient appearing here. But because of this controller, so these are all smoothened, and these are the corresponding active and reactive power. So the meaning here that despite either a connection or a reconnection of a DG unit from the system, and quickly the controller takes care of the transients and going back to the nominal values. So the summary of this work is that we propose some dynamic new controller, dynamic average consensus based control, and the results show that the proposed control restores the voltage and frequency effectively with change of communication topology, and it sustains the latency and also scalable for higher systems, and it supports the plug and play operation, meaning if any of the DG units goes wrong, still it takes care of, system takes care of. And then but we are looking forward for a asymptotic kind of convergence. So therefore what we did, we are trying for how to make this convergence faster. Now after designing that, we thought that let us design a robust adaptive controller which will give a more effective response. So here the objective is to regulate the voltage and frequency and achieve the desired active and reactive power sharing among the DG units, while supporting the plug and play and handling abnormal situation in face of uncertainties and disturbances. So what we did here, we considered that the voltage and the current across the DG unit and the bus, they are not precisely known. And also we assume there are some uncertainties in the PWM switching function of the VSI, and there could be some disturbances in the local load, and there could be fluctuation across the bus bar. So there were uncertainties and disturbances. So therefore, we wanted that we should design a controller so that all these DC units voltage and frequency are regulated to their nominal values. Of course, for that we integrate a observer called extended state observer. The meaning of the extended state observer is that it estimates the disturbances in a lumped manner, and then after integrating the ESO with this backstepping controller, we verified the stability of this controller using the Lyapunov theory, and of course we applied the multi-agent system. Therefore, there is a graph theory, and this paper recently appeared in IEEE Transaction Smart Grid. Now, this is the microgrid model. That means we consider a PV system as a one DC unit, and this is the DC-DC boost converter and a VSI, a filter circuit, and then the line impedances. Of course, it is connected to the point of common coupling. And as I said you earlier, the voltage and current controller. Of course, here our focus is the secondary controller. Now we derived the equation for the PV array interfaced with the converter with these equations, and then you also get the VSI dynamics integrated to filter. Both the equation we take and integrate all of them, and a state space representation we make. All the 13 states came, and then all the 13 states, and then the output is the, so the inputs are the modulating the PWM modulating signals. So then what we do is we put a communication in between. So this is the jth unit, this is the ith DC unit, this is the jth DC unit, and then we have this point of common coupling, and all unit have individual controllers. So we then considered an example where we have taken 4 DC units along with their loads and all that. So we put the communication network in between them, and then we calculate, as I discussed, we calculated the integrity matrix and adjacency matrix and Laplacian matrix. Then once you do that, we proceed with our controller design, in which we consider this modulation index of the uncertainties of the PWM switching function, and of course the load voltage variation and the busbar voltage variation are the disturbances. So once we do, we then we also integrated a the extended state observer here. This is the dynamics of the state observer, and we have to find out this observer gains G1, G2, G3, and then this is the structure of our observer based controller, backstepping controller. And these are few equations. Those are intermediate equations by which we get the final backstepping control UI. Then we evaluate the performance of this controller for different angles. One case study is that by variation of the irradiance of the PV array, how the voltage varies and corresponding power varies, and we put a DC link capacitor, and that DC link capacitor how to regulate the voltage with this controller, and how to bring down the THD of the inverter output current, and THD is found to be very less, 1.66%. And then what we did is we implemented the droop controller with unequal droop coefficients for voltage and frequency. What we did is we chose for 2 DC units with a voltage droop coefficient of 4% and frequency 1%, and remaining ones 5% and 2%. As you could see, the voltage and frequency and corresponding reactive and active power, large fluctuations are there, variations from the nominal values are there. But once we have chosen to the equal droop coefficients, they are now gone, and we are getting the the nominal voltage is achieved, and the frequency 50 Hz is achieved, and also there is not much fluctuation in the active and reactive powers. We also verified when you change the load, when we vary the load, the controller, the voltage and frequency, and corresponding this the power ratio deviation ratio, that is minimum power switching this deviation, and this is the active power deviation and reactive power deviation. You could see it brought down to 0, meaning the equal sharing happens among all the DC units. And then we also verified the plug and play operation, meaning one of the DC units DC number 2 is kept out of the loop, and then there is a transient, and quickly it is coming back to normalcy. Same thing reflected in the active power and reactive power, and these are the corresponding power transfer characteristics. We also evaluated the communication topology change effect. That means the controller is very good to change this topology from this to this one, and where you see all the DC output voltages are going back to the normalcy, normal voltage, and the frequency also with a allowable limit. And these are the voltage and corresponding the frequency. So here also we verified the effectiveness of the controller for two different plots of faults. One is the line to ground and the line to line. In both the cases, these are the voltage and current deviations because of the left side one is the line to ground and the right side is the line to line. And you see the deviations here. And but quickly it is set right to it is kind of regulated to nominal voltages because of the controller. And then we also compared the performance of this controller with some of the existing controller like distributed averaging controller and the centralized controller. So you could see the red one. It is very this is following the 50 hertz. Of course, there is a deviation here, and the voltage is also coming to this red one. We intended to maintain it at 350 volt, so it is happening. Now, what we did is we then experimented it. What we did is we have taken some, panels, simulator and panel both, and we have our all these sensors, etc. And we created this simulation, real-time simulation, in putting a polarity for the execution, real-time control execution. And this is the corresponding sketch of this, this experiment, and these are the parameters chosen. And this is the real-time simulation result, as you see. So like a lot of when the controller is not there, lot of this inverter voltage is output is like this. Now after this controller is added up, so this is smoothened, and now this is the result when some of the load is decreased and then some DG2 is plugged out, and how quickly the the voltage and frequency are regulated to the nominal values. And this is with these two controllers, the proposed controller, the one, even if there is a load variation and one of the DC unit is taken out of the loop, still very quickly the output voltage of the DC unit 2 is maintained at the nominal value. So the conclusion remains like this, that we propose some distributed controllers, and those are robust and adaptive in the sense they take care of the uncertainty in the system, and also in face of all those uncertainties and disturbances, we get the objective accomplished. And then the controller effectively handles the uncertainty and modeling errors also and disturbances, and the simulation and experiment both evident that the plug and play operation can be supported. Sorry. And some references for this work, and I must thank my PhD student Sonam and Swagat. Sonam is student here. Swagat is IIT Goa student who is going to submit soon. And of course, I should thank DST Government of India to support a lot with a imprint project, with a project of that is called CRG project. So all that money, I developed a microgrid there in IIT Goa. And the Sonam, while he was a student, she was a student here, done something with simulation. But experiment we conducted in this Goa, and it is quite interesting. So this is some of my experience at both the institutes at Rourkela and Goa in terms of the microgrid control. And one more student is now working towards in this area. Her name is Arunima. She is working in a different area. I am because it will be more bulgy if I put all of them together. So she is working basically the event triggered control. The idea is that how best the denial of services and cyber attacks can be taken care by these controllers. And recently those work are accepted by some IEEE transactions. And the other student who is working on this area, because this is an imprint project, we have promised to do something, and fortunately we got 2 patents granted, and one product also we had, that is the electric vehicle integrating the microgrid. The challenge we faced when you go for some more than 300 amperes of charging, it becomes very difficult because sometimes we burn our kind of the thermal problem is there. And fortunately we are now happy to see the negative excursion of the current, how to take it for consideration. It should be completely negated, and therefore the circulating current is prevented. So some of the good initiative have been taken, and these are all my experiences. With this I invite any question about this lecture what I made. I'll be happy to take some of them. Yes, please. Yeah, that's a very good question, of course. Actually, if you see the recent literature, unlike the other observer, I have chosen the extended state observer. What it does, all these, stochastic or distributed, all these kind of disturbances as a lumped parameter. So thereby it estimates the disturbance as an additional state, and thereby the dynamics is augmented as a augmented dynamics. It takes care of.
Okay.
A very interesting state observer. Extended state observer.
So the disturbance, the nature of the disturbance, like the randomness, it
Yeah.
can be like randomness can be it can follow Gaussian distribution. It may or may not follow the Gaussian distribution.
Yes.
So if we take in lumped parameter form, so like
Yeah,
what
that
can
is a
be,
question mark. Either you take any kind of representation, Gaussian or something,
Mhm.
but our objective is not like that. Our objective is the any disturbance appearing in the system. We are not taking care of the the stochastic out nature of it. But we are taking the distributed nature to bring it to a long, like the transmission lines, like that kind of thing. Okay. Of course, that can be thought of. You can
Okay.
think of. Yeah.
Thank you, sir.
Yeah.
Condition if we consider fault.
Can you use the microphone here? Yeah.
Sir, if we consider fault at the PCC point, then can it handle
Fault.
fault?
Yeah, we considered that. Nah? Fault tolerance control is there. Both control. One DG unit with the PCC, we create a line to ground fault and then we verified. We did it.
Sir, actually, one query is that you are actually changing the load in between, right? So what type of load you have been considered?
So load, unfortunately, we have not taken many nonlinear, only
Sir.
one, RL plus a diode we have taken.
Okay, sir.
We have not taken any electric vehicle or any sensitive load.
Okay, sir.
Only RL we have tried, RL plus a diode load.
And then other question is that as you are using that power electronic device, and then so how you are actually managing that reactive power control here?
Active power control.
Yes, sir.
Oh.
Reactive power. As you can see, that nonlinear load is actually that consisting of some maybe load, maybe you are using resistive or maybe inductive. How you are actually compensating that, reactive power.
No, actually that aspect is not taken care of here. Okay. Here the aspect is like this. In the microgrid, let us say there are 10 DG units.
Okay.
And each DG units there is a load demand. So based on the load demand, which ratio, which proportion these participating DG unit will share the load. That part we have considered.
Okay. So means the diode and then the resistive load you have been taken, right?
Yeah. Resistive and inductive also.
Inductive also. Yeah. All right. Yes. Any other?
Hello. Thank you for your interesting talk. Why do we require a communication network among DG? Like if the idea is you are assigning different costs at DG, or like it's just to reach the average of initial conditions and you get average average of voltage?
Yeah, that is a very good question actually. Actually if you look at the traditional grid and the smart grid or microgrid, the only big difference it makes in terms of the communication. Suppose the communication indirectly it says, suppose there are the net metering for example, because in the pro consumer, so you generate some electricity, you also use the electricity. So there must be a two-way communication. So this is one example. The second one is, suppose there is a change in some behavior dynamics. So immediately there must be a communication, right? So once you get a communication, then obviously the control will be, so basically we want to implement the multi-agent system control as I mentioned. So communication means every component must be communicated. Their information must be captured to the sensors. Okay. So communication is a must to make it smarter.
Thank you, sir. Thank you for your valuable speech on different control aspects of microgrid. Now I request Professor C.K. Chanda, sir, TPC Chair, ICS PCRE, to felicitate Professor Bidyadhar Subudhi, sir, Director, NIT Warangal. Thank you, sir. Thank you very much. I thank all the participants. After this, we will be starting with the technical session. Anything else?